Neural networks for rainfall estimation from multiple sources. Rainfall estimation is an important task due to the dependence of many people on it, especially in the agriculture sector. Rainfall estimation is difficult and even more complex due to the dynamic nature of rainfalls. Here, we would use satellite and radar data for rainfall estimation. Scanning radars can observe the four-dimensional structure of precipitation. Neural network is a non-parametric method to represent the nonlinear relationship between radar measurements and rainfall rate. The relationship is derived directly from a dataset consisting of radar measurements and rain gauge measurements. Here is a comparative study to investigate the performance of rainfall estimation based on radial basis function neural networks using radar reflectivity as input and rain gauge as the target data. When ground-based observations are sparse or infeasible to measure, satellite data is predominantly used. An approach is presented here in which cold cloud duration (CCD) imagery is used in conjunction with numerical weather model analysis data as the input to an artificial neural network. Principal component analysis would be used to reduce the data requirements for the weather model analysis and the use of a pruning technique to identify the redundant input data. Investigating rainfall estimation from radar measurements using neural networks. Data is collected from Melbourne, Florida NextRad Next Generation Weather Radar, which is ground radar data over the years of 2006 to 2009, and along with that, rain gauge measurements are also used to conduct various investigations. A direct gauge comparison is done to represent the improvement brought in by the neural networks. The PCA, Principal Component Analysis technique, is used to reduce the dimensionality of the training data set, which will reduce the training time as well as reduce the network complexity, which will also help us to avoid overfitting. Here is a representation of reduction of data from two-dimensional to one-dimensional, and here from three-dimensional to two-dimensional using principal component analysis. Radial basis function (RBF) neural network for rainfall estimation. The radial basis function neural network is a part of the multi-layer feed-forward neural network, in short MLFNN class. The MLFNN contains three layers, which are the input layer, the hidden layer, and the output layer. The RBF is used as the activation function in the hidden layer. The input layer accepts the input vector x, which has x1, x2 up to xp vector elements, and the hidden layer consists of m neurons with hx as transfer function. Input or target of the RBF neural network. Radar data, radar reflectivity factor ZH, will be used as input to the neural network, and the rain gauge measurement corresponding to that input will be the target of the neural network. The radar measurement of interest is the radar reflectivity factor ZH at the horizontal polarization. Now these are the ZH values at 1 km, 2 km, 3 km and 4 km in height with 1 km of horizontal resolution. These are the data locations for 4-point input vector. This shows the area covered by the radars and the rain gauges. The data is collected from the region shown here. Hidden layer. The transfer function h of x was chosen to be the Gaussian RBF given by hj of x equal to exponential of minus summation I equal to 1 to p xi minus cij whole square by rij square. And the output f of x can be calculated by a linear combination of the hidden layer outputs as follows: f of x equal to summation j equal to 1 to m wj into hj of x. Now here cj is the center vector of neuron j, and each cj has p parameters, and rj is the size or width vector of neuron j containing p elements, and m is the number of neurons in the hidden layer, and wj is the weight of the neuron j to the output layer. Adaptive RBF neural network for ground radar rainfall estimation. Now, to include the information from the new data at the end of each day, the multi-layered feed-forward neural network is updated by adding and removing some neurons. If the new data carries similar input data with different output, we just need to recalculate the weights from the hidden units to the output unit. This is the representation of the dynamic neural network, which is updated on a daily basis as shown. Performance of the adaptive RBF neural network. Adaptively training the neural network. The target of the network was the rain gauge measurements. These were collected from the tipping bucket rain gauge networks around the radars. Input training data, which was the radar measurements, it was taken at 1 km, 2 km, 3 km and 4 km in height. Thus, the size of the input vector is 4 as p equals to 4, and the rain gauge data were averaged over 6 minutes to meet the radar sweep time. Below is the representation of how the neural network is trained. This is the input data and this is the target data. So we train the neural network with the input data, and then we compare it with the target data to find the accuracy of the neural network. Testing and validating the neural network. Once the network is trained and we have new observations available for the next day, then this data is used to estimate the rain rate using the neural network that was previously trained. The estimation was validated against the rain gauge measurements of that day. Performance evaluation. The performance of the network was calculated using the following metrics. Here, frac bias, correlation NSE and NRMSE. These stands for fractional bias, correlation, normalized standard error NSE and normalized root mean square error respectively. RFN and RFG used here denote the estimated rainfall from the neural network and the actual rain gauge measurements respectively, and NG is the size of the data. The network performance was also compared with the simple ZR relation. Here Z equal to 300 into R to the power 1.4 used in the next-rad radars and with the best fit against gauge measurements. Fitting was done based on least square approximations. Best fit method was based on finding the coefficients a and b of z equal to a into r to the power b that would best fit z and r. The neural networks score higher correlation and lower normalized root mean square error, while the ZR scores lower correlation and higher NRMSE, which means a lower variation from the truth rain gauge measurements. The proposed technique has good scores compared to the best fit method as well. So the ZR relation has significant bias compared to the rain gauge measurements. There is the neural network product has a very small bias. These are the scatter plots for actual rain gauge versus the ZR rainfall estimate, the actual rain gauge measurements versus the best fit rainfall estimate, and the actual rain gauge measurements versus the neural network rainfall estimate. The data used is of hourly rainfall accumulation from the year 2009. As is evident from these graphs, the neural network rainfall estimates are closest to the rain gauge estimates as compared to the ZR estimates and the best fit rainfall estimates. These are the standard deviation plots for actual rain gauge versus the ZR estimate, the actual rain gauge versus the best fit estimate, and the actual rain gauge versus the neural network estimate. Again, we can say that the variation in the neural network estimates is lesser than the best fit rainfall estimation and the ZR rainfall estimations. Thus, it is proved that the neural network rainfall estimates are better than the ZR and the best fit rain estimates. Using principal component analysis to reduce the input size to the rainfall neural network. The input radar reflectivity factor Z is explored by applying principal component analysis over the standardized values of Zi, where Zi equal to the radar reflectivity factor measured at height I. Standardization is necessary due to the different range values Zi might have. The standardized values of Zi are given by Zi minus E of Zi divided by root over var of Zi. Ei is the sample mean and var of Zi means the variance of Zi. We define the sample covariance matrix of the standardized Z values, which is shown here, and using the sample covariance matrix, we calculate the eigenvectors E and the eigenvalues of the covariance matrix. After that, we calculate the principal components that are associated with the eigenvalues. PCA reduces the dimensionality of the training data to a level where we can still get good performance. To get the benefit of this concept and to reduce the dimensionality of the training data, we are going to choose only those principal components whose eigenvalues accumulation is larger than the threshold value chosen. The ground radar reflectivity factor, that is the Zi values, are collected at the 4 different height levels as shown here, 1, 2, 3 and 4 kilometers. Now first PCA is used to reduce the dimensionality of this data. We get 4 principal components and only the 1 and 2 principal components are chosen as the eigenvalues accumulation is larger than the threshold value chosen. Then the neural network is trained using these 2 PCs and rain gauge values is used as the target value. Using PCA, significant improvements were achieved in computation time almost 50% less than the time spent using the previous input configuration, and also it maintains the statistical metrics. Here in this table we have shown the fractional bias correlation, the normalized standard error, the normalized root mean square error, and the network size for the full radar data and using only the two principal components. So now we would show here a neural network approach to real-time rainfall estimation for Africa using satellite data. So here we would use a new approach based on the application of artificial neural network to a combination of satellite imagery and data from numerical weather prediction model analysis. So here rain gauge data is collected daily from 35 gauges in Zambia, located in Central Africa, covering an area of 750,000 kilometers square over the period of October 1995 to April 1999. Also, thermal infrared images and cold cloud duration (CCD) images are collected from geostationary satellites. Here, the locations of the gauges used for the calibration and validation during the study is shown. This area shows the location of Zambia in Africa. The thermal infrared images and the cold cloud duration images have been collected from the TAMSAT archive. TAMSAT is the Tropical Applications of Meteorology using satellite data and ground-based observations. Initial Artificial Neural Network Algorithm, TAM-ANN1. The kind of neural network here is a feed-forward multiple-layer perceptron MLP. In MLP, each node receives output only from nodes in the preceding layer and provides input only to the nodes in the subsequent layer. Thus, for the node J in the kth layer, the net input LKJ is a weighted average of the outputs of the k-1th layer. IKJ is calculated as summation of I equal to 1 to n k-1, W k-1ij, O k-1i. The W k-1ij is the weight connecting the output of the node I in the k-1th layer to the node J in the kth layer. And nk-1 is the number of nodes in the k-1th layer. So here we can see the input layer, hidden layer and the output layer in an MLP. So the output node J is a specific function of LKJ. OKJ is equal to function of LKJ. The eventual output is then a function of the weighted combination of the final hidden layer output values. Inputs to the MLP. The initial list of inputs included PIR pixel values and the spatial variance as well as CCD data. PIR means the thermal infrared image is pixel values and the CCD data is the cold cloud duration data. Location coordinates and NWP model parameters. The initial network architecture consists of 3 layers, the input, output and a single hidden layer, as shown here in the diagram. The transfer function relating input to output was a sigmoid function. So OKJ equal to 1 plus exponential of minus 2 LKJ whole to the power minus 1. This is the sigmoid function used for the input to the output. To ensure that a model has similar sensitivity to changes in various inputs, all of the inputs were normalized to values between 0 and 1. So, for an input variable x with maximum x max value and minimum x min value, the normalized value xA is calculated as x minus x min divided by x max minus x min. Okay. The optimum weights are determined by training values available to train the 500 input weights. It is therefore necessary to reduce the size and complexity of the network. Here we can see that there are 49 input nodes, 10 nodes in the hidden layer and 1 in the output layer. So, there are a total of 500 weights in the initial ANN. Now, the quality of the network performance is defined by mean square difference, MSD. MSD is equal to 1 by NT into NP into summation equal to 1 to NP summation T equal to 1 to NT of RAPT minus RKPT whole square, where RAPT and RKPT are respectively the ANN estimate and the Kriged estimate for the gauge pixel T on day T. NT is the number of days and NP is the number of pixels. Now, final artificial neural network TAM-ANN2. Now, using a technique called network pruning, the network is trained to a set of training data with an additional criterion of minimizing the number of weights. Now, this is achieved through a complexity term defined as Z. So, Z is calculated as summation of I equal to 1 to N1, summation J equal to 1 to N2 of W1ij square by WO square divided by 1 plus W1ij square divided by WO square, where W1ij are the weights connecting the input and the second layers, and WO is an empirically determined scaling parameter for the weights. N1 and N2 are the number of input and second layer nodes, second layer or hidden layer nodes. And the cost function, the total cost function to be minimized for the optimized network using network pruning is then C equals MSD plus Z. The learning rule changes the weights according to the gradient of the entire cost function C, continuously reducing the error under the constraint of a low complexity network. The effect is to suppress the weights of the redundant nodes. Input parameters associated with small weights may then be eliminated. So here is the representation of the optimized ANN shown here. Principal components of meteorological analysis fields of cold cloud duration, terrain information is fed to the neural network. Here we have 30, in the optimized ANN we have 30 nodes in the input layer, 6 nodes in the hidden layer and 4 nodes in the 6 and 4 nodes in the 2 hidden layers and 1 node in the output layer. This graph shows the mean input weights for optimized ANN algorithm. Weights are shown for 5 principal components of relative humidity, horizontal velocity, U, and vertical velocity, altitude, height, H, and CCD at temperature threshold. Comparison of results. Quantitative comparison is based on several statistical parameters. These are bias, root mean square difference RMSD, normalized root mean square difference NRMSD, explained variance R square, and skill. The definitions are below. Here are the formulas for the calculation of bias RMSD, NRMSD, R square, and skill. In these equations, RE is the estimated rainfall for event E, and RKE is the corresponding Kriged gauge pixel rainfall, and epsilon KE is the error on the Kriged gauge pixel rainfall for the same event. The value ME is the number of events over which the statistics are calculated and an over bar indicates an average over all the events. Comparison of results. The statistics for TAM-CCD, TAM-ANN1 and TAM-ANN2 over the years are given in the tables below. It can be seen that at all space and time scales and for all statistical parameters, TAM-ANN1 performs least well and TAM-ANN2 is slightly but consistently better than TAMSAT. Comparison of results. Now here we have the scatter plots of rainfall estimation by the optimized ANN against the correct pixel data for all time scales. The first one is for pixel day rain validation for all years. The second one is for daily pixel mean data, and the third one is for the 10-day pixel mean data. The solid lines indicate a one-to-one relationship. Here we have represented the time series of daily average rainfall for 1997 to 98. We have represented the mean correct data, the optimized ANN data, and the TAMSAT or the TAM-CCD data. Here on the top left we have the rainfall estimate from the optimized ANN. On the top right we have the rainfall estimate from the TAMSAT or the TAM-CCD. On the bottom we have the CCD images, the cold cloud duration images at different times of the day. And for the rainfall estimates, the range is from 2 mm for the gray regions and 30 mm for the red regions. The references used here are shown. And thank you for listening.